So, hi everyone. Today we'll have Amartya from NISA talk to us about equivariant K-theory and revisiting orientations. Amartya, the stage is yours.
Thanks for the introduction. Firstly, am I audible? So I hope everything's fine with the audio. Just want to make sure. Am I audible to everyone?
Yes.
Okay, cool. Thanks. So yeah, if there's an audio issue, if you don't hear me for a moment, I'm gonna be pretty chitty chatty. So if you don't hear me, just let me know. So I hope this doesn't happen again. Okay. So yeah, again. Uh, so right. So most of this talk, most if not the whole of this talk, would be based on Gepner-Mayer and Lurie's spectral algebraic geometry and elliptic cohomology too. Right. So there's nothing original, which goes without say, but I just wanted to make sure I say that at the beginning. Right. So here's the outline of the talk. So right. So there'll be just some recap, just just to make sure everybody's on the same page. Right. And then I'll talk about equivariant K-theory. So the first subsection, that is the classical story, that'll be mostly chit chat that I'll do. I don't want to spend a lot of time in this part. And as I was about to say, so that makes a couple of supersections. So we have three sections, and then for the equivariant K-theory, we have three subsections. And so that means that we'll have two supersections. So the first part is basically equivariant K-theory, which is subsection one. And then the second part, which is, as you can see, it's just an introduction to loads and loads of definitions and machinery that we'll use basically in the later part of the seminar. So let's begin. Right. So so let's recall what the goal of section 3 was. So the goal of section 3 was to get something like this, to get something like this, a pre-oriented abelian group object and some suitable infinity category X. We want to associate to it a co-limit preserving functor. So A is the category of anima. So just I'll say that. Right. So let's recall the construction that we had, the main construction from the last talk. Right. So so we start off with the finitely complete infinity category, and then the shifted Pantreigen duality functor. Okay, maybe I'll try to write less and I'll try to be a bit more efficient from now on. Okay, the shifted Pantreigen duality functor, basically that looks like this, right? So it takes values in, yeah, fin, right? So so if you want to recall what this fin means, so you have a so recall that you have a Laverre theory T, right? Which so TS fin looks something like this, just to recall. So this is like the smallest subcategory of TS, which I don't know, which contains the three T algebras on one object and is closed under the finite colimits, right? So yeah, just to recall that. And so now, so now we have the functor that looks like this. All this is from the last talk, so I'm just gonna write all this real quick. Which then, using the shifted Pantreigen duality, gives us a functor from previous. Right. So this functor looks like this. right? So now we have functoriality, right? So what does that mean? So that means that, like, if we have so we have functoriality. Uh, so what that means is that so if we have a functor, say from x to y, which preserves finite limits, right? Then we have a commutative diagram like this that looks like this. Right? For y. Right. So now we assume that the x that we have, so this character x, this is co-complete, right? So then given then for some then for z in the left gone along this inclusion, right? So this will basically induce a functor of x, right? And yeah, we can then extend this to. So this is basically, like, everything that we had in the last talk. Right. So now okay. Now I'll talk about some. I'll give you some the classical picture of equivariant K-theory. So this will mostly be fairly elementary stuff. I mean, just to motivate things, and I don't know, just for fun, I guess. So so roughly speaking, from what we know about uh, K-theory, equivariant K-theory. So it should be a way to study G vector bundles, right? G vector bundles. So I believe Siegel first generalized the notion of K-theory to the equivariant setting, and that means that, like, okay. So let me write something. Classical story. Right. So so you have a compact Lie group, and so then a G space is basically, like, I'm just recalling a few things. So a G space is just X, a space X with a continuous G action. So we are basically starting from rock bottom, like from the very basic. Then we'll see how technical things get, like when we move to the setting for our talk. But I want to start pretty basic, just to build intuition. So this is the way we think, right? So let's define it. G vector bundle. So maybe I can skip through these things, but let's go through. Let me define these. A G vector bundle in X is a vector bundle where E has the structure of a G space, right? And E is equivariant. So throughout the talk, like, I'll just use this for equivariant equiv. So that means it's equivariant, right? So also we want the maps, and fibers to be linear. That's pretty straightforward. And so we get a category of G vector bundles on X and G equivariant maps. Right. So let's maybe see an example. So yeah, so this H is a closed subgroup. Then basically we have an equivalence of categories between G vector bundles on X, G vector bundles on X, and finite dimensional H representations. So yeah, without further ado, since this is fairly classical stuff, let's move forward. So then so then basically we get a functor between equivariant G vector bundles on G quotient H to H representations, right? So we get a functor like this. This maps to H. So, right. So the category of equivariant vector bundles as a G space X naturally forms an additive category, right? It's an additive category. So basically define so this is the way we define the equivariant K group. So it is just the Grothendieck group of equivariant vector bundles on X, right? So basically, so this kg of X, so this is basically a contravariant functor in X under equivariant maps of spaces, right? Right. So now, so what else I want to say? So now let's recall that. Okay. So okay. Now we've seen so far that we have there exists an equivalence of categories between between equivariant vector bundles on G quotient by H and H representations. So this kg of G, so this kg of G, just it's just equal to represent H representations, right? So now okay, I just remark maybe. So we have this fairly important relation between equivariant K-theory of space and K-theory of quotient. So you have this. This is like fairly classical stuff, so I'll just state it. So yeah, if G acts freely on X, I guess. Yeah. Right. So okay. So yeah, maybe right. So that means that we kind of have this is like a natural map that we have. So maybe okay. Let's move to the second subsection. So I did not start with. Okay. So maybe. Oh yeah. So yeah, the second subsection. So now we'll basically talk about some multiplicative infinite loop space theory and like how that arises in our setting and I'll just illustrate how it's useful in basically how we use it. I'll just try to give an example. So I'll basically give the non-equivariant example. The equivariant construction is also similar, but since I understand the non-equivariant version better, so I'll just give that example, right? So now, okay, so let's start. So this is the subsection 2, I believe. So, okay, G is a compact Lie group. So this is our category of compact Lie groups, and then basically G representation. So this has the structure of an E infinity semi-ring category. So what does that mean? So what do I mean by E infinity? So an E infinity semi-ring in C is basically. Yeah. So yeah. So here's what I mean. And right. So now, yeah. So now right. So now we'll see why we need this multiplicative infinite loop space theory. And so again, so this will be a very general kind of speed run. I mean, kind of a speed run through the whole theory. But yeah, so I recommend for people interested, most of this theory in the infinity categorical setting is due to Gepner, Groth, and I believe Nikolaus, right? So yeah, so we can maybe talk about that more after the talk, if anyone's interested. But right, so the upshot is that why do we care about this multiplicative infinite loop space theory is that right. So we'll use that to get so yeah. So we'll use that to get KUPG, right? So so this is our infinity ring spectrum that basically de-loops for the group completion of. So yeah. So yeah, that's the point. So now let's talk about this multiplicative stuff, right? So as I said, it will be a speed run. So and for a better reference, by the way, like if someone's interested, then better reference, I believe, is there's this recent paper. So I was suggested this by Leonard. Like Leonard suggested this. So this is a paper by Bastian, Runa, Toby, and Sil, I believe. So yeah, again, more about that later. So right, let's start. Multiplicative. So we start off with a closed symmetric monoidal presentable infinity category and infinity upright. Again, so a disclaimer is that like if there's something, it's fine to black box a few things if you have an issue with something, but at some point, like towards the later part of the subsection, I think everybody should be fine. But okay, then we basically have the group completion functor between the commutative monoids on C to commutative groups in C. So this is my notation. And associated to it, we have the spectrum functor associated to this. Spectrum functor that basically looks like right. So right. What else do I want to say? So yeah, these basically refine. Yeah, these basically refine to the following functors. So these two. So let me call this star hash. So star hash refined to functors between theta semirings in C. I know we've basically defined this. And this is a category of theta rings in C. So what do I mean by that? So this basically is like theta algebras. Right. So this is called the this is called the ring completion functor. And so yeah, this and another one that we get looks like this. So this is basically called the ring spectrum functor associated to the ring completion functor. Right. So now let's consider. Okay. So again, we've fixed this A. So this is the infinity category of anima, and then cat is the infinity category of ordinary categories, and yeah, then sub-infinity is the infinity category of infinity categories. So using the last theorem, right, using the last theorem, the group completion and the associated spectrum functor, so that basically looks like this. We're using that for the case of anima, basically. So these refine to functors that look like this. So this basically gives us a way to get highly structured ring spectra, right? So right. So now for algebraic K theory, we basically have an input which is like a symmetric monoidal category. Say, okay, let's write this. So maybe I'll say this is a remark for. Oops, I'm sorry. For algebraic K theory, input is like a symmetric monoidal category. So say let's call it M, right? So like so for example, like if you okay, I'll just write this. Right. And then so this is like symmetric monoidal with direct sum and coproduct, right? So now if so now we consider the subcategory of isomorphisms. Okay, consider. So this is just an example. So now consider the subcategory. So let's call this M tilde. So yeah, subcategory of isomorphisms. Let me write this. Subcategory of isos, right? And then pass on to the geometric realization, right? So then basically we define algebraic K theory, the algebraic K theory spectrum, So this is basically the spectrum associated to group completion of this geometric realization. So that means that we get something like this. Symmetric monoidal categories. Basically geometric realization. Right, we're basically sorry, my bad. It's supposed to be a subscript. Spectra. Right. So this basically gives us the algebraic K theory functor, right? So now we basically we have an analogous construction for like other variants of K theory as well, right? But yeah, so this was basically a speed run through the non-equivariant version, like how you basically construct algebraic K theory. So maybe a remark I'll add this because this is very important. So this K theory functor is lax symmetric monoidal. So that basically means that it induces a functor in theta semi-rings to this. So theta is basically an infinity operator, right? So Clark-Bowick basically. So okay, I don't remember the reference, but maybe we can talk about references after the talk. So Clark-Bowick basically shows that you can basically like this so if you consider the algebraic K theory of Waldhausen infinity categories, right? So the algebraic K theory of Waldhausen infinity categories. So this is also lax symmetric monoidal. So okay, that ends the detour. So we already spent almost half of my time after all this. So okay. So remember that we had an E infinity ring spectrum, BG, that basically deloops the group completion of the completion of right. So now we can refine this to a functor. So we can define these representations to a functor. Like E infinity. Okay, so let me write this. Right. So how, you may ask, like, how do you do this? So basically, so here's the deal. So G representations, you can basically identify. Okay, maybe I'll just say this aloud. G representations you identify with G, right, on BG. So it only depends on the Orbi space BG, right? Oh, whoops, my bad. Sorry about that. Okay. So basically, KU refines to a functor up to here. So now, as UPTS KU, so by the way, just want to clear up the notation. So for me, this is K in uppercase, and this is K in lowercase, just to prevent confusion. So this is my capital K. Okay. So okay, right. So we get refinement. So that means that we basically define this functor. So this is basically, so we define this as, so using this KU functor that we had. Right, so this is the way we kind of define it. And so, right. So let's see. So now, okay, so now here's how things work. So let's see. So the G fixed points of P, G. So this basically represents equivariant K-theory. These agree with and then by Bott periodicity, in the equivariant setting, basically, of course. So you get that KU G to G induces it induces equivalences on infinity loop spaces. So now now via limits, we can basically extend this KU up to 2. And then the pi 0 of the resulting KU. So this basically agrees with the classical G equivariant K for X, which is some, I don't know, some GCW complex, I guess. So right, okay. So now, okay, here's the main part. So this is the third subsection, that is equivariant K-theory in our setting. How do we recover equivariant K-theory from whatever we've defined throughout the seminar, right? So right here. So let's recall Lurie's definition of a strict multiplicative group. So what I'm saying, Lurie, throughout the talk, most of the time references are elliptic cohomology 2 or maybe spectral algebraic geometry, but I think for this one it's elliptic cohomology 2. So here's the definition. So an abelian group object. So we define an abelian group object GML affine spectral schemes as follows. Just write it down. Right. So this is equivalent to this mapping space right here. So again, remember this is a anima. Very careful anima. So now the group structure basically, so it comes by seeing this GM of R as a okay. So if you're thinking of it as a function from T to A, so that's basically where the group structure comes from, right? So moving on. So now we define something called GM, maybe S, for an E infinity ring S. So this is basically we define as the non-connective spectral affine scheme. And why basically? I mean, it might seem a bit random, but the reason is pretty simple because this basically, GM is co-represented by, I'll just write it. It's co-represented. Okay. So now, so this is the key theorem for the first section of the talk, and so the next few minutes we'll try to prove it stepwise. So we have a pre-orientation. Okay, all right. Such that the functor that we constructed last time, and so this one basically, yeah. So this is equivalent. This one. Moreover, so extending via the co-limits, so this gives us an equivalences of functors on A odd basically, right? So the proof. So the proof basically has two main steps as you might find in Kaplan-Meier, right? So here's step one, and the way I see it, for me, the step one's not that hard, but step two is a bit technical. So probably we'll see. We'll see if I can at the moment, on the go, if I can flesh out all the details right now. But let's see. So here's the claim. So Q is unextended from E. Right. So we first state a lemma, without proof, which we'll basically use for the step one, right? So you start off with a factorization system. On some, I don't know, some infinity category C, and the X is in C. And you consider C star as it is a full subcategory, such that for all Z in C prime, every morphism, so it goes to X. So this basically factors as follows, where this Z prime is in C prime, and F is in L, and G is in R basically. Then the inclusion of the full subcategory of X on the morphism lying in R, right, is finite. So again, so there's a bit of a notational kind of I don't know, hodgepodge, I guess. So this is in higher topos theory, this notion of finality. So Lurie calls it cofinite. So that basically means that functors that induce an equivalence of colimits indexed by the source and target trading categories. Right? So yeah, that was the lemma. So now, so now this is lemma that will actually prove. So now let's define F to be a family of groups which is closed under isos, subgroups, and I guess quotients. So I think Etna and Maya call it global families, I believe, if I'm not wrong. But okay, I'll just stick with this. So whenever I say a family of groups or whatever, so if I forget to say that it's closed under iso, subgroups, and quotients, that means that it is. It is. Right? So okay. So let's define. So this is the full subcategory on PG. So is that G. Okay. Now fix some compact Lie group G and R. So this is a full subcategory, this R, on representable maps. Right, that means that like those which correspond to injections basically. And right, okay. So thus, this inclusion is fine. Then this inclusion is fine. So right, so I'll just give a rough sketch of the proof, right? So we recall that we have I don't remember if we've seen that in the seminar, but we have a factorization system on OP basically. So for a homomorphism from H to G, BH to BG is in the left class, even only if phi is surjective, and it's in the right class. It belongs to the right class if and only if phi is injective. So factorization systems correspond to factorizations of this phi as, so basically this sits inside G. So this basically, this clearly restricts to, okay, this clearly restricts to, for any such family F, the way we've defined F. So now by the last lemma, then basically we use the last lemma to prove this finality. But so this lemma that we have, we use this to prove. So okay, by last lemma. So now here's a proposition. And this is due to, if I'm not mistaken, okay, I'll probably have it in my notes. So I believe this is due to Adams, Habach, then Jakovsky, and I believe May. Yeah, right. So, okay, so this is a proposition. C algebra is right con extended from op for a family of groups. Again, so when I say family, it's closed under isomorphism, subgroups, and quotients, right? With all topologically cyclic groups. Okay, let's see the. So okay, particularly here's the important part. Okay, I was almost about to forget. Particularly the family of abelian compact Lie groups. This is what we're going to need actually. So here's the proof. Okay, so first you basically consider a full subcategory G of representable morphisms EH to G. So now using the last lemma, so this is basically final. So which means that G of is initial. So what we want, so our goal is to basically our goal is to show that UPG so this is an equivalence. So using this, it suffices to show that KUPG is an equivalence. So now for this, we'll actually have to use a fact like that I'll just state without proof, I guess. I just don't have the time to go through all the technical details. But here's the fact. So G is a compact Lie group, and we have a fully faithful embedding. Right? But yeah, the proof's not hard. It's easy. So with the essential image, with the essential image morphisms, which are basically representable, I guess. And right, so okay, using this for this inclusion that we have. So this if you remember, this is basically the full subcategory H with so that this H is in the family. Also, moreover, this co-limit that I hope I don't mess up. By the way, feel free to point out mistakes. I might make a lot of them, but I hope I don't. But this co-limit is a universal space. So let's call this EF for the family of subgroups that are in subgroups of G. Okay, that looks pretty bad. Let me rewrite that again. EF for the family of subgroups of G that are in F. So that implies, if you take the limit, that is basically true. This EF that we define to be this universal space, basically. So now these people, Adams, Havak, Tarkovsky, and May prove that for a G map, say from X to, I don't know, Y, restricting to a homotopy equivalence. H for all cyclic subgroups H is F star. This is basically an isomorphism. So basically, right. So basically using this we'll get that this point. So this is an iso. And that basically implies the result. So remember this was the result. Right. So it's right connection from that basically implies gives us the desired result. So okay, that was the step one. So I'll try to move through step two a bit fast. Maybe I'll skip a few things because really out of time. So now, okay, how do we get a choice of a pre-orientation on? So choice of pre-orientation KU. So here's a basic fact. So this KU. So this is a group completion of, and so that is basically. So that means that this U of 1 KU. So this is the, oops. Uh-oh. Oh no. Okay, maybe I'll pause the recording for a moment. So here's me messing things up. Okay, so I'm starting a different app because I suck at using iPads, presumably. Okay. So how do we get a, so this is a step two. So how do we get a choice of pre-orientation on choice of pre-orientation on U? So okay, maybe for time purposes, maybe I'll skip through the proof of this, but okay, but no, okay, I think it's important enough to, I think it's just, let's go through this. So okay, so this is, we know that this FKU is the Cyrus to completion. Oopsie. Okay. This is bad. So basically, one, two, U. So this is the resulting E infinity map. So this is adjacent to a map. The objects of basically, right? So yeah, this is basically our choice of pre-orientation on GMKU, right? So now the next part is next part of this step is basically so it's a bit technical, so I'll kind of just state it. So the rough idea is basically that rough idea is that all irreducible G representations for an abelian group G are one-dimensional, which means that KU PG. Right. So here's the main proposition that I'll state without proof. It's a bit technical, and you can find all the details, I guess, in Shekhar. So this functor, the functor, so that basically takes here I might say something stupid. So I have to be a bit more careful. Okay, yeah, so this is basically equivalent to a functor that, I mean, that maps same source to same target, but that looks basically like this. See, I'll just keep R. So the corresponding result for Ku like follows from here basically, right? So that implies that spec of Ku is equivalent to here, Ku. Right. So this is basically the final object of our fine Ku schemes. Right? So from these two propositions, we basically get our main theorem. Like, if you want me to flesh out the details more, so maybe we can do that in the post talk session or maybe later, because that's quite technical and it's going to take a lot more time. Right? So okay. Now we move to finally to the second part of the talk, and I'm seeing that I've really less amount of time left, so I'll kind of speed run through this and try to not be my own worst enemy. So okay. So now we'll have a lot of definitions of machinery that I'll basically introduce for our next upcoming couple of talks, where we'll see the explicit construction of equivariant elliptic cohomology, right? So okay, what's the point of this section? Basically, the point is that that's the first thing that you might ask, right? So the point is basically that, like, although it's sufficient, like, so far we have based on this pre-orientation theory. So this is basically sufficient for defining equivariant elliptic cohomology, right? But for but for a lot of properties, like in really good properties, we kind of need to start with an oriented elliptic curve, right? So we need to kind of develop the formalism. So okay, so the goal is basically define an infinity topos of sheaves. So again, I want to make this a bit more clear that so there's a lot of definitions that I'm going to state to this, so that might be a bit hard for people to digest. It was certainly hard for me to digest. So if there's something that you cannot follow, just don't worry about it. It'll be fine. So okay, so define an infinity topos. So okay, here's the goal: to define an infinity topos of sheaves on a given non-connective spectral Deligne-Mumford stack. Okay, so so from now onwards, I'll call this non-connective spectral Deligne-Mumford stack. Okay, here let me write this down. Okay, and for okay, I'll just write it down here. By the way, I'll make sure the notes are a bit more polished when I'm uploading it to the website, so you don't have to worry about it. So, and spectral Deligne-Mumford stacks I'll denote by spec EMS, right? Just to save some time. So okay. So now to avoid, like, a lot of size issues, that so if you have a decent background in spectral algebraic geometry, if you've read stuff by Louis, and, like, if you've worked in settings like this before, then you know that there are a lot of size issues. So you kind of impose some finiteness conditions. So here's what we do. So we use this kind of notation. So I'll denote this MOM by just this usual M, and so this by this. Right. And okay, so let's start with the formalism. So let's start with, so this will mostly be a lot of definitions, and we'll basically develop the formalism. So non-connective spectral Deligne-Mumford stack M is quasi-compact if every cover, say VI, in, okay, this is, remember this, so in M has a finite subcover. Right. Okay, now here comes a few more definitions. So a morphism of spectral Deligne-Mumford stack. So by the way, if you want me to recall what I mean by spectral Deligne-Mumford stack, it is just a non-connective spectral Deligne-Mumford stack where the structure sheaf is connective. I mean, just that, just as simple as that. So it is called almost of finite presentation. So for those of us who have tried to read spectral algebraic geometry, we might have heard of this. So, and that's related as well, you'll see. If it's locally, so that might ring bells, almost of finite presentation in the sense of SAG, right? So, and quasi-compact. So I'll just quickly explain what that means for people who have not seen. So what do I mean by locally almost of finite presentation? I apologize for my handwriting. I know it's pretty bad. So, okay. So you consider a morphism. So here's what I mean by locally almost of finite presentations. You consider a morphism of spectral Deligne-Mumford stacks. So F is locally almost of finite presentation if for all commutative diagrams where you're basically taking the étale spectrum of B and étale spectrum. So this is a morphism F, and this and this. So these are basically étale maps. B is of finite generation over A, which is pretty classic stuff. Over A. So yeah, just want to make sure everybody's on the same page. Okay, so a few more things. So for a spectral Deligne-Mumford stack, the big étale site is a full subcategory of spectral Deligne-Mumford stacks over M. So okay, let's call this M. That are almost finitely present. Almost a finite presentation. And the coverings are basically given by, I believe, jointly surjective étale morphisms. Right? So now let's define this to be the infinity category of space valued sheaves on the big étale side of M. Right. So basically, if instead of a spectral Deligne-Mumford stack, if you have a non-connective spectral Deligne-Mumford stack, then it is basically so if M is non-connective spectral Deligne-Mumford stack. So this is basically this. Oh, okay. So now we come to the definition of an elliptic curve in this setting. So I can see that I'm out of time already, and I believe I have a few more things to say. So apologies for that. But there are a few more things that I have to introduce. But I'm pretty much done. So it's probably going to be 10 more minutes, I guess. Okay. So what else? Okay. Yeah, I was about to define what an elliptic curve is. Okay. So you fix a non-commutative spectral Deligne-Mumford stack, then an elliptic curve E over M is an abelian group object, and the infinity category of non-connective spectral Deligne-Mumford stacks over M says that this map is flat. Again, this is like SAG terminology, but okay, maybe let me try to remember. Okay, yeah, I think, yeah, let me recall what that means. So this x to y is flat. So yeah, for all these definitions, the reference is basically SAG and elliptic cohomology. So, but for this, it is I believe SAG, right? So if for all commutative diagrams, you take the étale spectrum of P, and you take the étale spectrum of P, and these two maps are étale. So then the underlying map of P infinity, like, as far as A to B, is basically flat. So that basically what this notion means. And so this doesn't seem to be a very good definition, as you'll see. I mean, not easy to think about it, but I'll say something in a moment. This is almost of finite presentation that we define as proper. So what do I mean by proper? Again, it's a lot of terminology. So what do I mean by proper? So let me define this. So again, you consider a map from X to Y. So it is proper if it's three things: quasi-compact, separated. Oh no, four things, I believe: locally a finite type and closed. And number three, for all morphisms, K. Okay, let me not say K. Let me use something else because I'm using this lowercase k for. So spec of this is basically algebraically closed classical field, just an algebraically closed field. Pull back. There's a classical elliptic curve. So I mean, the way to think about it, you basically view an elliptic curve E over M as an abelian group object in the category that we defined, the infinity category of space value sheaves on the big étale side of M, right? So by using the functor of points on the tau of E, basically. Okay. So now fix a non-commutative spectral Deligne-Mumford stack M and an elliptic curve P from E to M over M. So here's another definition. A pre-orientation of E is so what do I mean by pre-orientation of the notion of elliptic curves that I defined? It's pre-orientation of E as an abelian group object and this category. So the one that we define basically. Sorry. So that is, it is a morphism of abelian group objects. Right. So now we'll define the, okay, what's left? Okay, yeah. Let's define the formal completion. So this is the formal completion of E. So this is basically an object category. So you basically define it as follows. So this is open relative spectral subscheme. That's a complement of the closed unit spectrum. So, okay. So now, suppose M is a spectral Deligne-Mumford stack, and if then okay. Now we are about to define formal hyperplanes. So it is, so this F is a formal hyperplane. So where was a formal hyperplane? If it's a form. So okay, I did not define relative co-spectrum. Okay, I'll just write it and I'll just define what that means. So this is relative co-spectrum. Okay, so this is basically so this is called the relative co-spectrum of coalgebra C, right? where C is a commutative coalgebra over M, right? So how do you define this? So this is basically equal to space. So this is the category of commutative coalgebras over A. So and R is basically infinity ring. So yeah, that is smooth. So what do I mean by smooth? Smooth basically means that C is of form N for some discrete ring R and some n greater than 0, and this map is basically, this is an isomorphism for all k in Z. Okay, so we're almost there. Now there's a lemma. So for all spectral Deligne-Mumford stacks, this co-spectrum functor that we defined, the co-spectrum functor defines an equivalence between the infinity category of smooth coalgebras on M and formal hyperplanes on M. So like, for example, for every elliptic curve, say E over a non-commutative spectral Deligne-Mumford stack M, this formal completion is a formal hyperplane. So that basically should explain how to think about it. So let me see, do I have something? Okay, yeah, there's a few more things that I have to define. So let's recall. So an E infinity ring R is said to be complex periodic. I mean, maybe I'll just say this. So it is said to be complex periodic if it's complex orientable first, and then it is, and then Zariski locally, basically, there exists a unit in pi2 of R. So it's a complex periodic. I'll maybe write it later. And for a complex periodic infinity ring R, the Quillen formal group is defined as follows. So maybe there's a Q here. So now, like, so I'll say one thing and then I'll end by the last definition. So there's some work that you can do. So you can actually show from I think the reference is elliptic cohomology 2, if I'm not wrong. So you can basically show that this Quillen formal group, basically, that we defined. So it is a formal hyperplane and abelian group object. So how, maybe we'll talk about that later. So right, so maybe this will be the last definition of the talk. So you take a locally, so we basically end by defining orientations. Locally complex periodic, right? And E is you have pre-oriented elliptic curve. Sorry about that. Over M, and E is oriented if is the formal completion is an equivalence. So I hope it is not too boring, but yeah, with that I'll stop. That basically ends my talk. So thanks for listening.
Let's thank the speaker. Are there any questions? No? Okay, so maybe we can stop the recording, Amartya, and maybe there will be post-recording questions.
Okay. So, yeah, thanks everyone.